In this video, we'll talk about tangent line approximations and differentials. If f is a differentiable function, then the derivative at a is defined in terms of a limit. F prime at a is equal to the limit as h goes to 0 of a difference quotient, f at a plus h minus f at a divided by h. One way of interpreting this definition is that f prime of a is the slope of the tangent line at the point with coordinates a, f at a. The fact that f prime of a is defined as a limit as h goes to 0 means that if h is very small, then the derivative of f at a is approximately equal to that difference quotient. That is to say that f prime of a is approximately equal to f at a plus h minus f at a divided by h as long as h is very small. In terms of lines, that means that the slope of the tangent line is approximately equal to the slope of a secant line passing through the point a, f at a, and another point close to it. So this point right here has coordinates a, f at a, and then we imagine that h is a small number, so you increment a by a small amount to a plus h, and this is the x-coordinate of another point on the curve. So on the curve, you have a point with x-coordinate a plus h and y-coordinate f evaluated at a plus h. And if you draw a secant line through these 2 points, then its slope will be approximately the same as the slope of the tangent line through your initial point. Since both lines pass through the point a, f at a, if their slopes are close enough to the same, then the lines almost coincide with one another. And the closer that a plus h is to a, that is, the smaller that h is, the closer these 2 lines will be to overlapping. If x is a number that is very close to a, then we can write x as a plus h for some number h close to 0. And then we have that f prime of a is approximately equal to f at x minus f at a over x minus a. And indeed, the limit of this difference quotient is f prime of a as x goes to a. If we rearrange this expression, basically solving for f at x, then we have that f at x is approximately equal to f prime at a times x minus a plus f at a. And this approximation gets better and better the closer x is to a. If we use the right-hand expression here to define a function, call it L at x, so that L at x is equal to f prime of a times x minus a plus f at a, basically just taking this expression on the right and calling that L at x, this gives you a function of x, which is called the tangent line approximation or the linearization for f at a. And the graph of L is the tangent line to the curve at the point a, f at a. So here we have the curve, and we have a point a, f at a, and through this we draw the tangent line. This tangent line is the graph of y equals L at x, where L is that tangent line approximation or the linearization. The output of L is a y value corresponding to a point on the line. So if we look at L at a plus h, that gives us this point right here, and that corresponds to a y value, L at a plus h. And the basic idea is that these 2 values, f at a plus h and L at a plus h, should be close to each other so long as h is close to 0, so long as a plus h is close to a. And that's what we have here. So here you have that f at a plus h is approximately equal to L at a plus h, as long as h is really close to 0, so that a plus h is close to a. So this little difference right here is our error term. As an example, let's determine the tangent line approximation to f at x equals the square root of x at x equals 4. So the tangent line approximation, L at x, is equal to f prime at a, in this case a is going to be equal to 4, times x minus a plus f at a, which is 4. A is equal to 4. So we just need to determine what all of these pieces are. So we need, for example, the derivative. We know what f at x is. It's the square root of x. I'm going to write that as x to the 1/2. And then we differentiate that using the power rule. F prime of x is equal to 1/2 x to the minus 1/2. And now we evaluate both of these at 4 in order to get the values f at 4 and f prime of 4. So f at 4 is the square root of 4, or the positive square root of 4, which is 2. F prime at 4 is equal to 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. Here I'm just rewriting this term as 1 over 2 times the square root of x. This gives us everything that we need. So L at x is equal to f prime of 4, which is 1/4, times x minus 4 plus f at 4, which is 2. And this is our tangent line approximation to the square root of x at x equals 4. When x is close to 4, the value of the square root of x is approximately equal to the value of this linearization, which is 1/4 times x minus 4 plus 2. And you can see that we have the square root function graphed here, and we've also graphed the tangent line. This tangent line has equation y equals 1/4 times x minus 4 plus 2. And you can see that as long as you're close to 4, as long as your x values are close to 4, then the output of the square root function is very close to the output of the tangent line approximation. Let's do another example. Determine the tangent line approximation to g at x equals e to the x at x equals 0. So we're going to do this the same way. The linearization is equal to g prime at a times x minus a plus g at a. Now in this case, a is equal to 0. So we know what g at x is. It's e to the x. And g prime of x, of course, is also e to the x. The derivative of e to the x is just e to the x. We need to evaluate both of these at x equals 0. So g at 0 is e to the 0, which is 1. And g prime at 0 is e to the 0, which is equal to 1. Because, of course, g is its own derivative. So if you evaluate both of them at 0, you're going to get the same thing. So now we just plug all of this in. L at x is equal to g prime of 0, which is 1, times x minus 0, plus g at 0 is 1. So if we simplify this, we have that L at x is equal to x plus 1. And if we graph both of these, you can see that when x is close to 0, then their outputs are close to the same. So here we have this curve is y equals e to the x, and this dashed blue line is the tangent line, which is y equals 1 plus x. And as long as your x values are close to 0, then the output for e to the x and the output for 1 plus x are close to the same. Now, if you start straying far away from 0, so if you are even here at 1/2, you can start seeing that these two diverge from one another. And so the error will get more and more and more. But as long as you're close to 0, then these two curves are very close to each other. And so that means the y values for a given x are close to one another. That is, for values of x close to 0, e to the x is approximately equal to 1 plus x. Let's do another one. Determine the tangent line approximation to h at x equals sine at x equals 0. So again, the linearization is going to be L at x is equal to h prime at a, which again is 0, times x minus a plus h at a. Basically, the idea here is that you're looking at h at some value, some known value, and then you're going to vary from that value by a small amount. This is the distance away from a. X minus a is the distance away from a. But you're changing at a rate which is equal to h prime at 0. So you're starting at h at 0 and then you're varying by a small amount at this given rate. Okay, so what are these quantities? Well, we know what h is. H at x is sine of x. And h prime of x is the derivative. The derivative of sine is cosine. So we want to evaluate these at a, which is 0 in this case. So h at 0 is sine of 0, which is 0, and h prime at 0 is cosine of 0, which is 1. So we just plug all of this in. L at x is equal to h prime of 0 is 1 times x minus 0 plus h at 0 is 0. So actually simplifying this, we just get that L of x is equal to x. And indeed, for x very close to 0, sine of x is approximately x. As we can see from this graph, we have the graph of sine of x here and the graph of the tangent line. Indeed, for values of x close to 0, sine of x is very closely approximated by x. The difference between f at a and f at a plus h is usually denoted by delta y. We think of this as the difference between y values, f at a plus h minus f at a. So f at a is the y value at a, and then f at a plus h is the y value after you've incremented the x value, going from a to a plus h. So the difference between the x values is delta x, and the difference between the y values is delta y. So the value of delta y is the change in the output values of f at x over the interval from a to a plus h. And the change in input over this interval is usually denoted by delta x. But notice that delta x is just h. It's the distance between a and a plus h. In this picture, delta x is a positive number, but that's because h is positive. Similarly, delta y is positive, but that's just because f is an increasing function. If h were negative, or if we were looking at a decreasing function, then one or both of these values, delta x and delta y, might be negative. The difference between f at a and the approximate value of f at a plus h is denoted by dy. So whereas delta y was f at a plus h minus f at a, dy is L at a plus h minus f at a. So in our picture, we have that delta y is the difference between the first output value and the second output value of the function f. But dy is the difference between the first output value and the approximation of the second output value. So dy is the difference between f at a and L at a plus h. dx is also a quantity, but it's just the same as delta x. The value of dy is the approximate change in the output values of f at x over this interval from a to a plus h. Once again, it's possible for dy and dx to be negative. The advantage to using dy over delta y is that it's easier for computations. Dy, remember, is the difference between L at a plus h and f at a. Now, L at a plus h is f prime at a times a plus h minus a plus f at a. This a plus h is our input, so that goes right here. A plus h is our x. But notice that we have an a here and a negative a here, so those will cancel, leaving us with just h. But h, remember, is dx. So in our picture here, h is the difference between our two input values, a and a plus h, but that's also something that we're calling delta x or dx. That's where this dx comes from right there. What else do we see here? We have an f at a minus an f at a. Those terms will cancel, and what are we left with? We're left with f prime of a times dx, which is this. But f prime of a is just the derivative at a, so that's easy to compute. That means that dy is just simply the derivative of f at a times dx. We have names for dx and dy. These are called differentials. Differentials can be useful in computations. For example, consider the following plot of the unit circle with central angle theta radians. In this picture, we have a central angle measuring theta radians, where the initial side of the angle is the positive x-axis, and the terminal side intersects the unit circle in a point, and that point, of course, has coordinates cosine theta and sine of theta, where the x-coordinate is cosine and the y-coordinate is sine. Now, we imagine drawing a tangent line at this point, and we're going to increment our theta by a small amount, which we'll call delta theta. Now, since this is the unit circle, then the measure of the central angle in radians, which is delta theta, is the same as the arc length of the intercepted arc. So this circular arc length is delta theta. Now, if we just imagine this tangent line here between these 2 points, we'll call that d theta. D theta is our best linear approximation of delta theta. So this is our initial point with coordinates x comma y, and then we move along the tangent line a small amount to this point. So this is our linear approximation of this point right here. So if we measure the difference in x between our initial point and our approximate point, then the difference in x values we call dx, and the difference in y values we call dy. Now, in fact, this dx is actually a negative value. We're calling it dx, but in fact, that's the length is the absolute value of this dx. This dx is actually a negative value because our initial point is to the right of our approximate point. This dy is a positive number because we're moving up. Now, here is a very useful fact, which is that this small triangle right here is similar to this larger triangle right here. Now, why would that be true? Notice first that they're both right triangles. They both have a right angle. So here is the right angle in the large triangle, and here is the right angle in the smaller triangle. The other thing is this angle right here and this angle right here. This radial line is perpendicular to the tangent line. So that tells us that this angle right here is a right angle. That's a right angle. Another right angle, so let me actually just mark it with a different color. So this angle right here is a right angle. And if I change the color slightly, this angle right here is also a right angle. And notice that these two right angles have this angle in common. So if we call this angle, let's say, alpha, then alpha plus this angle is 90 degrees. And this angle plus this angle here is also 90 degrees, so that means it must also be alpha. So we have two right triangles that have one angle in common. That means their other angle must also be in common. So this angle must be theta. So this angle here is theta. So what we have is we have two similar right triangles. Now these two similar triangles will reveal an important relationship. So just to mark them again, remember that this is one of the triangles, and then the other one is this triangle right here. These are similar triangles. And remember that this angle is theta, and the other angle we were calling alpha. So what are the sides that correspond to one another? So for example, we have the hypotenuse, which is d theta. That corresponds to this hypotenuse, which of course is the radius of the circle, so that length is 1. What other side correspondences can we mark? Well, we have this length right here, which starts at angle alpha and goes to the right angle, so that corresponds to this angle, which is dx. But this height is the y value, which is sine. So that means that this length right here is sine of theta. And furthermore, if we just change our color, we have that this length going from theta to the right angle corresponds to this one going from theta to the right angle. So that one is length dy, and that corresponds to this length, which is cosine of theta. Because cosine of theta is the x value, which tells you how far along the x-axis you've gone. So now we can use the relationships between the sides of these similar triangles. So we know that corresponding sides of similar triangles are in equal ratio. So that tells us that, for example, dy to cosine theta is equal to d theta to 1. So dy to cosine theta is in the same ratio as d theta is to 1. Okay, well, if we just rewrite this slightly, if we take this cosine theta and put it up here, and then divide by d theta, we have that dy d theta is equal to cosine theta over 1, or just cosine theta. But what is y? Remember that y is sine of theta. Y is sine of theta. So what we've just established is that the derivative with respect to theta of sine of theta is cosine of theta, using a very nice geometric argument. Similarly, we can show that the derivative of cosine of theta is the opposite of sine of theta. And for that, we have to be a little bit careful with our minus signs, because if we measure the common ratio, we might write down dx to sine of theta is equal to d theta over 1. So now we're looking at dx to sine of theta, and that's in the same ratio as d theta is to 1. But at this point, we have to remember that dx is actually a negative number. So in fact, this is the opposite. This is equal to the opposite. And that's why when we then cross multiply, we end up with dx over d theta is equal to the opposite of sine of theta. And of course, x is the cosine of theta. So what we've established is that the derivative with respect to theta of cosine of theta is the opposite of sine of theta. And that comes about simply because dx is actually a negative number, so this has to be negative as well. This d theta is actually the length here, so that's a positive number. But dx is actually negative, so the only way that these two ratios can be the same, since one is positive and one is negative, is if we put a minus sign here. And that's actually where this minus sign comes from, in front of the sine. And that's why the derivative of cosine of theta is the opposite of sine of theta. or at least that's one way to see it. But this is a very nice geometric approach. It is possible to come up with better approximations. The tangent line is the best linear approximation to a function. That is, it's the best way to approximate it using a line. But sometimes it is not as good an approximation as other times. For example, the tangent line approximation for f at x equals cosine x at the point where x is equal to 0 is the horizontal line y equals 1. And that's simply because we have a peak here. So we have a peak, and when you have a peak like this, the tangent line is horizontal. That's because the derivative is 0 there. So this tangent line doesn't very closely approximate cosine, or at least not perhaps as well as you would like, because you have to be very close to 0 in order for this to be an approximation. It's not nearly as good as the one that we had for sine of x, for example. So how do we improve it? And the way we improve it is by looking at more terms. The tangent line approximation to f at a is the unique linear function that has the same derivative as f at a. If we want a better approximation near x equals a, we can find the quadratic function that has the same not just first derivative, but also the same second derivative. For example, cosine of x is approximately 1 minus x squared over 2, and this is a much better approximation to cosine near x equals 0. The approximation is still only good near to x equals 0 because this is a parabola which opens downward, so it's unbounded going towards negative infinity as you move to the left or the right, whereas cosine of x is always bounded between minus 1 and 1. So it isn't a good approximation everywhere, but it's a good approximation near x equals 0, and it goes out a much further distance than our original linear approximation did. You can show that this quadratic function, 1 minus x squared over 2, has both the same first derivative and second derivative as cosine of x. And that's why it hugs the curve much better than just the tangent line did. We can do this with other functions. So for example, if we look at y equals e to the x, that's this curve here, we saw that it was fairly well approximated with just 1 plus x. But if you add in a quadratic term, so it's 1 plus x squared over 2, now we have a function which is a polynomial function of degree 2, and it has the same value as e to the x at x equals 0, and it has the same first derivative and the same second derivative at x equals 0. And that's why it hugs the graph of y equals e to the x much more closely. And again, it's only valid as an approximation close to 0, but this is a better approximation over a larger interval. Polynomial functions are often easier to work with than other functions, so sometimes approximating a function using a polynomial will make computations easier. So a polynomial function that you use an approximation in this way has a name. It's called a Taylor polynomial. So a polynomial function that has the same first n derivatives as f at a is called the nth degree Taylor polynomial of f at a. And these are very useful for doing approximations.